What if I told you that every single number has a secret code, kind of like a unique numerical DNA? And at the very heart of this code are these special building blocks, prime numbers. They are literally the ingredients that build every other number out there. Today, we're going to crack that code.
So here's the game plan. We'll start with the building blocks themselves. Then, we'll get into the one simple but incredibly powerful rule that governs them all. After that, we'll see this rule in action. First, by making a familiar school task totally foolproof, and then by proving something, well, pretty profound. Finally, we'll tie it all together to see why this one idea is so fundamental. You see the pattern, right? First the concept, then we use it to solve a problem.
All right, let's talk about those special ingredients. In the world of numbers, your most basic elements are the primes. You know, numbers like 2, 3, 5, 7, the ones that can only be divided by 1 and themselves. Every other number, what we call a composite number, is just a mashup of these primes.
And this is true for every single composite number. A simple one like 253, yeah, that's just 11 times 23, both primes. But it also works for a huge, messy number like 32,760. If you break it all the way down to its core, you find it's just a bunch of 2s, a couple of 3s, a 5, a 7, and a 13, all multiplied together. Primes really are the atoms of arithmetic.
Okay, but this brings up a really crucial question. We know 253 is made from an 11 and a 23, but could it also be built from, I don't know, a 7 and some other prime? Is there more than one recipe for each number? The answer to this is what makes the world of numbers so unbelievably cool and orderly.
And that answer is found in one of the absolute cornerstones of mathematics. It's called the fundamental theorem of arithmetic. And, with a name like that, it's got to be a big deal.
And here it is. The theorem says that any composite number can be broken down into a product of primes. And, now this is the part that changes everything, that breakdown is unique. There is only one set of prime ingredients for any given number. Now, sure, the order can change. 2 times 3 is the same as 3 times 2, but the actual ingredients in the recipe, they are always the same.
What's wild is that, while this idea might seem kind of obvious to us now, it took centuries to formally prove. The ancient Greeks, like Euclid, they knew about it, but the first person to really nail down a rock-solid proof was the legend himself, Carl Friedrich Gauss. They didn't call him the prince of mathematicians for nothing.
Let me put it another way. The prime factorization of a number is its fingerprint. It belongs to that number and that number alone. No other number in the entire universe will ever have that same combination of prime factors. That's the power of uniqueness.
Okay, so we've got this powerful concept of a unique numerical fingerprint. But what can we actually do with it? Well, let's start with something you probably remember from school, finding the highest common factor, or HCF, and the lowest common multiple, or LCM. With this theorem, we have a completely foolproof method. The method is actually super simple. For the HCF, you just look at the prime factors the numbers share, and you take the smallest power of each one. For the LCM, you do the opposite. You take the greatest power of every prime factor involved, whether they're shared or not. Let's see this in action. We want the HCF and LCM of 96 and 404. So, step 1 is always the same. Find their unique prime fingerprints. When we break them down, we see that 96 is 5 2s and a 3, and 404 is 2 2s and a 101.
This little table here makes it really easy to see what's going on. We've got our prime factors listed down the side. You can see the only prime they have in common is 2. For 96, we have 2 to the power of 5, and for 404, it's 2 to the power of 2. Then 96 has its own 3, and 404 has its own 101.
So now, we just apply the rules. For the HCF, we need the smallest power of the common prime, which is 2, while the smallest power is 2 squared, which is 4. Done. For the LCM, we take the greatest power of each prime we see. So that's 2 to the 5th, 3 to the 1st, and 101 to the 1st. You multiply all that out, and you get 9696. No guesswork, just a clean, repeatable method.
So that's pretty neat for school-level math. But this theorem isn't just for simple calculations. Oh no. It is powerful enough to prove some of the deepest truths in mathematics, like the existence of irrational numbers, those weird numbers that you can't write as a simple fraction. To prove it, we're going to use a really clever technique called proof by contradiction. Think of it like being a detective. You start by assuming the opposite of what you want to prove. Let's say you assume the suspect is innocent. You then follow all the logical clues, and if you end up with a result that's completely impossible, a contradiction, then you know your first assumption had to be wrong. The suspect was guilty all along.
Okay, let's use this to prove that the square root of 2 is irrational. Step 1, we assume the opposite is true. Let's just pretend, for a minute, that the square root of 2 times is rational. That means we can write it as a fraction, a over b. And this is key. That fraction is in its simplest possible form, meaning a and b share no common factor.
Right, now let's follow the logic. If we square both sides of that equation and just move things around a bit, we get 2 times b squared equals a squared. Now what does that tell us? It tells us that a squared has to be an even number, right? Because it's equal to 2 times something.
And here it is. This is where our fundamental theorem swoops in to save the day. Because 2 is a prime number, the uniqueness of prime factors guarantees that if a squared is divisible by 2, then a itself must also be divisible by 2. It's the only way for the prime fingerprint to work out. So we now know a is an even number. We can write it as 2c.
Okay, stay with me. We're going to substitute that 2c back into our earlier equation. After a little bit of algebra, we find that b squared equals 2c squared. Hang on. That looks familiar, doesn't it? It means b squared is also an even number, which, thanks to our theorem, means that b must be even too.
And there it is, the gotcha moment, the contradiction. We just proved that a is even and that b is even. That means they both share a common factor of 2. But wait a minute, remember our very first assumption? We said the fraction a over b was in its simplest form and had no common factors. Our logic has led us to something completely impossible. Since our airtight logic led to a contradiction, our initial assumption must be wrong. The square root of 2 simply cannot be rational. Therefore, it must be irrational. And that, my friends, is a beautiful proof, powered by the fundamental theorem of arithmetic.
So, we've seen this theorem do some real heavy lifting. Let's just take a step back and appreciate why it really truly earns that name, fundamental.
So, why does all this matter? Well, first, it guarantees every number has a unique identity, its own prime DNA. It turns messy problems like HCF and LCM into a clear, reliable process. And as we just saw, it's so powerful it can prove deep truths about the very fabric of numbers. Honestly, it's the bedrock that so much of higher mathematics is built upon.
We'll end with this thought. If prime numbers really are the atoms of mathematics, our theorem gives us the laws of chemistry, how those atoms combine. But the primes themselves, they're still full of mystery. What other secrets about our universe are they just waiting for us to uncover?